So the second part of 2.6 is about what we call piecewise functions. Okay. Piecewise functions simply are functions that look like they've been broken up into pieces. So we looked at absolute value. All of them look like V's or upside down V's. We haven't seen any upside down V's yet. Okay. We've looked at linear functions, so straight lines, continuous. They go on and on forever. Okay. Now we're going to look at piecewise functions, and piecewise functions look like parts of all of that. Okay, and you have to analyze and treat each piece differently, separately, independently. They are all their own sort of functions. However, combined together, they create one piecewise function. Essentially, we're going to have one or more equations combined together with restrictions so that we can, each portion of the function gets treated differently depending on which area of the function we're considering. Here's the first type of piecewise function we're going to look at. Now, this is one function. Okay? Even though it looks like there's two equations and two inequalities, I'm going to explain why it's all separated like that. This particular function happens to have two pieces. This top line is the first piece. This second line is the second piece. They are joined together by this brace. Okay? This is to indicate it's only one function. So we're going to graph each part, and they should be two separate pieces, and then we're going to determine the domain and range. Now, in order to do this, here's what we have to think. So I'm writing this out, but this is supposed to think. Okay? What we're thinking is, for this first one, y, because remember f of x is like y equals x minus 2. But that's only for when x is less than negative 1. Okay? So there's a restriction. The function looks like this only when x is less than negative 1. All right? And also, the function looks a little different, the second piece, when x is greater than or equal to negative 1. So we put this little restriction. The shape of the graph will look like this for this condition. The shape of the graph will look like this for this condition. Now, the idea of graphing a line y equals x minus 2 shouldn't be hard to you, right? That's slope-intercept form. Shouldn't be really hard. All right. The idea of graphing the line y equals x plus 3, again, that's slope-intercept form, shouldn't be hard. But we're not going to graph the whole line. And we're not going to graph the whole line. There's a restriction. So instead of going on and on forever and ever from left to right, there's going to be a boundary. And on the next slide, I'll show you how to do that. Now, this is the same piecewise function here. I've put a boundary here for right now. It's going to go away. It's not, you shouldn't technically have that there. But I'm putting it there to show you because in this particular piecewise function, the restrictions are right near each other. All right? In fact, they're all based on this line. This is the line x equals negative 1. All right? So I have two things going on. All right? What I've circled in red, where it's less than negative 1, that function is going to be on the left of the boundary. The second part that I circled in blue, greater than or equal to negative 1, is going to be on the right side of that boundary because it's greater than. That's where it's greater. Right? So if this is negative 1, the values where x are less than negative 1 are over here. Okay? Less than negative 1. Where the x values are greater than or equal to negative 1, to the right. Okay? So the rule that I use for my graph on this side is here. The rule that I use for the graph on this side is here. And it's just a matter of doing that and graphing those. Okay? Now I'm going to show you two different ways to do this. And it's up to you to decide which way makes more sense to you. And from problem to problem, you might change from one method to another. Again, I'm leaving that up to you to decide which way is easiest for you to understand. So let's start with this top equation, okay? Y equals x minus 2. What is the slope for y equals x minus 2? 1. What is the y-intercept? -2, right? It's in slope-intercept form. No big deal. Okay? Now, understand sometimes it's not going to be in slope-intercept form. And you may need to create a table of values or put it into slope-intercept form in order to graph it. Okay? When I have the slope and y-intercept, notice I put the slope as 1 over 1, right? Because when I graph the y-intercept, because that's my next move. Now here's what's interesting. So I graph the y-intercept. Y equals -2, so I put a point there. Now this is technically on the wrong side of my boundary, right? Because this equation is less than or equal to -1. Well, this is greater than -1. What we do is we graph the line like normal, and you can either chop it off, and I'm going to show you how to do that, or you just only graph it on the left side of this line, x equals -1. Okay. Now, if I use the slope 1 over 1, I'd go up 1, right 1, up 1, right 1, and I'd draw a line right here. Okay. The problem is all these points over here aren't part of this rule. I really need points over here. So what I can do is use my number sense to change the slope from 1 over 1. How do I make myself move left? I can just change that slope to -1 over -1. And now, so notice I made the boundary go away. Okay, we don't need it anymore. It shouldn't. It was just sort of a visual. All right. So now, if I go down 1, left 1, down 1, left 1, down 1, left 1, I get a bunch of points. And I'm moving in the right direction. I'm getting closer to the left side of x, or left side of -1, less than -1. Now notice here I put an open circle instead of a point. Okay. Yep, because negative divided by negative is positive. Yep. So this, both of these equal 1. I just manipulated the slope to work in my advantage because I need points over here. Now because the x is less than -1 and not equal to, I keep an open circle here where x is equal to -1. Because it can't be actually equal to -1. It's just less than. So this is that same idea that we looked at in chapter 1, open circle, closed circle. You know, obviously this one's going to give me a closed circle. All right. So now I can just connect my points, and notice that I erased the y-intercept because this is on the wrong side of the boundary, right? This point right here does not go with this rule. So that's one way to do this, is to understand where the boundary is and only draw it on that particular side. The other way to do it, and I'm just going to draw over this, okay, is to actually draw that entire line the way I had it, like this, and let's say you just did count up 1 over 1, and you didn't do this at all, okay, and you draw the entire line, but then you have to figure out, okay, where's the boundary and where does it get chopped off? Well, the boundary is here, and all these things I'm going to end up erasing, okay. We know that the boundary is here. So that green line actually gets chopped off to the left because it's less than. So what you can do when you graph, and I'm going to put it in red again, is go, all right, open circle. Now I just graph my line, and I go back and go, all right, I'm going to get rid of that, get rid of my boundary, and I have my line again. So with notability, what you can do is draw the line again, and then only draw the part that you need, because the other parts aren't part of it. Either one is fine. I don't care which way you do it, but you're going to have to pick one of them. Okay? Now, Bless you. So that's just the first piece. All I've done so far is I've graphed that. Oops. There we go. I've graphed that. That's all I've done. Now I have to repeat the whole process for the second piece. Okay. So I have my equation. Okay. Y equals x plus 3. What's the slope? 1. What's the y-intercept? 3. Now, so there's my slope, there's my y-intercept, so I can graph my y-intercept. Alright? Now, if I use up 1 over 1, up 1 over 1, that's going to be okay because all of these points over here greater than or equal to negative 1. So everything on this side is greater than or equal to negative 1. So I can do that. Alright? Up 1 over 1, draw my line. Here's my only issue. Where does this part of the line start? For what x value? What is the x value right here? 0. Right? The x values have to be greater than or equal to negative 1, which means it really needs to start where x is negative 1. So in this case, since I knew my slope was 1, I could just go down 1, left 1, and sort of back it up a point and line it up. And that's the rest of the piece. Okay? Again, another way that you could do this I'm going to go back to that green like I had it, is use the slope and y-intercept. I guess I'm not going to go back to the green. There we go. Is to have my slope and y-intercept, graph the whole line, and then chop it off. Because I know that it has to be greater than or equal to negative 1, which means here at x, so I would just draw my line, go back in Notability, chop that line off, and I would get my graph there too. Okay? You can do it either way. You can just understand that, hey, I have a boundary, so it's only going to go so far to the left, and that's going to go on and on forever. Or you can graph the entire line and then shade over it or draw with a different color and just erase that line that you chopped off. Okay? Now, the idea of graphing a line is not hard. You know how to do that. Where to chop it off, that's going to be the tricky part for you. Okay? Notice that also that this point here was filled in because x can be equal to negative 1. Because x can't be equal to negative 1 up here, I have the open circle down here. The next thing that I have to do, find the domain and range. Okay? Now, here's what you're doing when you're finding domain and range. You're really looking for gaps. I'm going to start, for the domain, I'm going to start at the left, and I'm going to kind of move over to the right as far as I can, and see if there are ever any x gaps. Alright, so for the x's, let's start here. So I'm here at like negative 8, and I move to the right. Alright, so all these values are continuous. There's always going to be an x in here. Alright, the dilemma is right here. Is negative 1 on the graph?
Yeah.
Which one?
Blue.
The blue one. It's not on the red one. But right here, when it stops being on the graph, it jumps up to this one. So we're still good. Okay, and then as I move to the right, there's always an x value that goes with the graph. So what's the domain going to be?
All real numbers.
All real numbers. Okay. When I look at the y's, if I start at the bottom and move up, are there any gaps?
Yeah.
Yeah, there's a gap right in the middle. Okay. So the domain is all real numbers, but I have this y gap when I look at it from up and down. So what we do when there's that gap is that's how we determine where our range is going to be. I have two parts of my range. There's the red part when I start here and go down, and the blue part when I start here and go up. So if I was to write all these values for y and going down, what would it be? For the red part, what's the highest value here?
Just under negative
Right, so it's not quite equal to negative 3, so that's where it's going to be less than negative 3, because all these values down here, right? It's not or equal to, it's less than negative 3. And if you wanted to test it, you plug negative 1 in here. Negative 1 minus 2, that is negative 3. So in fact, this is exactly negative 3, but it's not equal to it, it's less than. Then if I look at the blue one, what's the lowest y value? What value is the y value here? 2. So again, if I plugged x in, which was negative 1, that's 2 and above. So greater than or equal to. So that's what my range looks like. It's 2 parts. You're either down below, where f of x is less than 3, everything from here and down. So think about those boundaries that we did with the absolute value. It's the same idea. Right here I have an upper boundary, so at negative 3 or below. Or it's going to be up here where I have a lower boundary where y is 2 or f of x is 2 or above. Question. So depending on how many pieces there are will likely determine how many parts of the range or domain you might have. Now that still doesn't guarantee that just because there's 3 pieces, there's 3 different ranges. Okay? 3 different inequalities for the range. It doesn't mean that it will be. They could be contained within them. Okay? Let's look at something else. So here's a graph of a piecewise function. Now we're going to do the opposite. We're going to write the equations for a piecewise function. So in the previous case, I gave you the equation. We did the graph and domain range. Now we're going to give you the graph. And we need to write the equation. So clearly, I have how many pieces here? 3, which means I'm going to have 3 different equations, all part of the one piecewise function. So first off, the first thing you're going to do is you start with your setup, okay? And you identify the 3 different pieces. So I start with f of x. They tell us that it's f of x, right? Right here, they tell us it's f of x. Equals, I make my giant brace because I'm going to need 3 different equations. And again, think of that as y. It's y equals, okay? And I've identified 3 different boundaries. So for this one, I have a boundary here and to the left. This one, I have these boundaries here in red. And for this one, I have a boundary here and to the right. And so the first thing that I recommend that you do is set up all your boundaries. So if you remember on the last problem, we said if x was less than negative 1, if x was greater than or equal to negative 1. What I want to do is come up with all the boundaries first and then worry about the equations. Okay? So let's start with the very first one. Okay? What is the x boundary there going to be? 1. Okay? Is it greater than, less than, greater than or equal to, less than or equal to?
Less than.
It's less than, and it's not or equal to because I see this open circle. So it's going to be if x is less than 1. Okay? So that's the boundary part. Just for that. All right? Now let's focus on the next boundary. Let's focus on this boundary. What is my inequality going to be for this?
X is 3.
So what's the left boundary?
X is greater than 1.
Greater than 1, and what's the right boundary?
3.
Just give me the numbers.
2. Less.
1. So my left boundary here is 1. My right boundary here is 2. So since it looks like kind of like an and, right? There's a left boundary, right boundary, we connect them in the middle. So I have a compound inequality. If 1 is less than or equal to x, which is less than or equal to 2. So I just write my boundaries out. Smallest one on the left, biggest one on the right. It turns into an inequality, a compound inequality, an and. All right, just like we did in chapter 1. Okay, then the last one. What's the x value associated with this line? 2. Since it's an open circle, it can't be equal to 2. It just can be greater than 2. So those are the 3 boundaries for each piece. That's the hard part, figuring that out. The rest shouldn't be too bad because they're all what type of functions? Each piece is what type of function? What does the graph of it look like? Say it. Linear, right? They're all lines. So the graphs are all linear functions. So now I have to just write each one out and use slope y-intercept to write my equation. So now we're in 2.4, writing equations. Okay? So in this first one, all right, what's the y-intercept there? For the first graph.
3.
1, 2, 3. The y-intercept is 3. Okay, so I put that in there pretty easy. Now I just need the slope. What's the slope of that line going to be? So if I counted up to right 1, rise over run, slope is 2, which means there's my first piece, 2x plus 3. Find the slope, find the y-intercept, and you write your equation. All right, that's the first part. Second part doesn't even cross the y-axis. How am I going to find the y-intercept? Like, where's this line? If I could continue it, where's it going to cross? The y-axis. 2. It's gonna be right here. Right? So I just back it up. Right? If I'm going this way, I go up 1, left 1. So just do that again. Up 1, left 1. Well, the y-intercept is 2. Now we just talked about the slope. Negative what?
1.
Negative 1. Okay? Up 1, left 1. 1 over negative 1. Okay? Or if I started up here and went down 1, right 1, either way, the slope's still negative 1. Okay, so that's negative x. This last one, if I backed this line up, where would it hit the y-axis? 3. It'd hit 3. Okay? And actually, that's it. It's a horizontal line. Horizontal line is always y equals something. The slope for this is actually 0. Okay? Horizontal line is y equals a constant. Vertical line is x equals a constant. Okay? So those are the 3 pieces, the 3 equations. Okay, in this case, they didn't ask us to find domain and range, so we don't need. And actually, your domain, this is always going to be your domain. Okay, in this case, there's no gaps, right? So less than 1, well, there's 1 covered there. To 2, there's greater than 2 covered there. In terms of the x's, there's no gaps. Right here, they cover each other. Right here, these x's cover each other. Everything that way, everything that way. Now, the range, if we were looking at the range, we would have a top value here, because there's nothing above there. So y would be less than 5. Is that 5? Yeah, that's 5. Y is 5. And below that, everything's covered.